Okay, so when we're talking about perceptrons and neural networks, it'll be clear throughout the course of the presentation that neural networks are essentially, we take the idea of a perceptron and we're going to extend this a little bit further. And what that is going to do for us is give us a universal function approximator, which is why these are used so widely throughout computer science right now. So the first thing we want to talk about is, well, where did we get this idea at all? Like, why do we have this concept of a neuron and why is it interesting to us? So that has a biological basis. In 1958, we had basically the idea of trying to ape the functionality of the human brain with this code abstraction. We wanted to come up with something that was going to be able to basically encode some of what the brain is doing. So we have neurons, and all of these neurons are interconnected to many, many neighboring neurons, and together this forms the structure of the brain. That's about as far as I can go into it because I'm not a cognitive scientist. But what we ended up encoding was essentially neurons fire if there are enough neighboring neurons that are connected to this neuron that are firing, and depending on the strength of the connection to each neuron. So if you're strongly connected to a neighboring neuron and it's firing very strongly, you want this neuron to fire as well. Whereas if this is only a weak fire or it's very weakly connected, then this neuron is not going to fire as well. So it's a very simple idea that we are going to implement mathematically. And the first way that we did that was with a perceptron. So perceptrons, this came about in 1958. A scientist called Rosenblatt released a paper about them. So a perceptron is capable of linear classification, and it's going to do some sort of classification between two binary states. So you can have something that the output is 0 or it's 1. It's very easy to see that any other binary classification task could just be mapped directly onto 0 and 1. So if you have something where it's true or false, class 1 or class 2, positive, negative, all of those things can be trivially mapped to 0 and 1. So here in this example, I'm going to be basically saying positive for 1 and negative for 0 interchangeably, because they are equivalent in this case. So our actual mathematical model of the neuron is pretty simple. We have this input or a feature vector called x. And that x is n dimensions, so it has n different features. These are going to be like scalar values. So if we were looking at like a prediction model, a pretty classical example is like, okay, I want to try to predict how much my house is going to sell for. You can give it some scalar, it has to be classification. So let's say we're trying to classify, is this thing a cat or a dog? So some of the things that you can give it are like, okay, how much does it weigh? How tall is it? How long is it? These are some scalar values that together make up a three-dimensional input vector. And then the class prediction y here is going to be, is it a cat or is it a dog? And then all the neuron is doing is it's saying, okay, I want to get some weight, so I pay attention. It's kind of like how much it's paying attention to this. How much do I think the weight matters? If like the pet weight matters. If I think that matters a lot for the classification, I want to give it a high weight. And if I don't think it matters very much, I want to give it a low weight. Similarly for like how long it is and how tall it is. So all we're doing when we calculate this output is, okay, we're saying this weight times this input, this part of our input, and then we're adding a bias to the entire activation. So equivalently in vector notation, this is just showing a dot product between you have some n-dimensional weight and an n-dimensional feature vector, and then the bias is getting added to that. And for the perceptron, what it does is very simple. It just has a threshold where it says, okay, we're using this heaviside function, which just says, let me show you what it actually looks like. So all the heaviside function is it says, okay, if I have a value that is negative, I just set the output to 0. And if I have a value that's positive, I'm just going to set the output to 1. And that's where we get our binary classification. So very, very simple. And this has a really nice geometric interpretation that I think is worthwhile to understand to get some sort of intuition for what it's doing, even as we move into neural networks, because it's just doing this in a higher dimensional space, essentially. So together, the weights and biases give us some sort of plane that just divides whatever our space of interest is in half, the binary classification. So in this example, I just want to show it for 2 dimensions. And for a 2-dimension, this hyperplane is just putting a line directly through our space. And on one side of the line, you have all the positive class predictions. That's to the upper right there. And then on the other side of the line, we have all the negative class predictions. In this case, the weights can also be thought of as the normal vector that's coming out of this plane, and the bias essentially is just shifting this. So the weight is defining the slope of this line, and then the bias is shifting it off of the origin in some direction. So really quickly, if we just wanted to go through that math, I just want to look at like, okay, we have this query point 42, and we can see clearly here that we should get a positive class label. But the math to see that as well is very simple. So we have this weight and the bias. Our weight is just 1, 1, the normal vector, and the bias is shifting it by 4. For this query point 4, 2, it's just the dot product with the normal vector, and then we subtract 4 off of it, so it's 2, positive. So we output the class label as 1. So this is an example. The previous one is, okay, we just were able to look at the data set. We drew a line that perfectly cuts it in half, and then we calculated that. Typically, we want our algorithm to be able to train and find where this boundary is without us having to give it any input. And that's just what this perceptron algorithm is doing. You have this big data set. You make an initial guess as to what the hyperplane looks like, and this is just directly through the origin. And then as you add for every single point, you're just going through and you're basically saying, okay, I'm trying to make the prediction with this hyperplane as it currently exists. And if it mispredicts it, then I'm just going to change the hyperplane so that it predicts this one correctly. And we're just going to do this for every single data point, going through our data set as many times until we can get through the entire data set without causing an error. So the hyperplane has stopped moving around, and now we just have our classifier. But there is a problem with this. It's obviously very limited. You don't typically have data that can be very nicely cut in half, where it's just perfectly one side is one class and another side is the second class. So that's, if you have data that does fit that description, where you can just perfectly separate it by a line in 2 dimensions or a hyperplane in whatever dimension, that means that you have linearly separable data, and the perceptron works fine with that. But if you do not have linearly separable data, so for example, a very famous example of this would be the XOR problem, where it's just saying, okay, if we have different signed X and Y values, then we're going to output a positive, and otherwise we output a negative. But with this, we can see clearly there's no one location that you can put a line through this that's going to perfectly be able to classify the 4 points shown here. So this is something that just the perceptron by itself can't handle. The data is not linearly separable. And what would happen if you were to try to train on this, it just never converges. Like every time you would put a new data point in, well, possibly not every time, but it's just going to keep moving it around. It will never find a line that separates them. Okay. A couple of notes before we move on from perceptrons. It is possible to basically cleverly link up some of these perceptrons so that you make a NAND gate, which is a very, very fundamental building block in digital logic. You can make any digital circuit, anything in your computer, using just NAND gates, and that is how they're implemented. So you can use them to create really interesting decision boundaries, but they are still fundamentally just collections of these hyperplanes. So for example, you could get a perceptron where if you put multiple neurons together, it has basically a yes, no is the data upwards of this line, and then another yes, no is the data down from this line. And then if both of those conditions are met, it will give you a positive class label. But it's not possible with just one single neuron. And then another point that I want to make is, so you have these weights, but it's not clear exactly like what we're learning from them. If you just are giving small perturbations in the weights, what that can do to your output is if you have a really negative output and you just change the weight a little bit, it's not going to change the class label. So it doesn't have an effect. if you're in a very negative space. And if you're in a very positive space, you're up here where it's outputting 1. You basically change the weight a little bit. It changes the output a little bit, but it's still up here. It's getting thresholded to 1. So changing the weight only matters if you're right around the point where it goes from 0 to 1. And then small perturbations will make a big change where it will go from outputting 0 to 1. So there's not like a nice like linear interpolation you're making as you're changing these weights. And that will change as we move to neural networks. But before we go on, I just want to show the Perceptron notebook example. So at the top of the page, the very first one is the notebook that we're going to take a look at here. And let me just pull this off a little bit so that it's easier for everybody to see. Okay. Okay, so what we have here, I adapted this notebook from Sebastian Roschka's Deep Learning Fundamentals course. All of them that we'll see today are adapted from the same link. And I would highly recommend, if you're interested in this, going to check that out, because it's just an excellent demonstration of all of these fundamental concepts implemented in PyTorch, which is, I believe, the most widely used library for implementing neural network architectures. So if you're interested in making your own, it's a great place to do that. Yes, let me send the link for this one. Basically, you can make AND gates out of NAND gates, but you can make any other logic gate out of a NAND gate. So if you're looking at like the smallest possible component from which you can make any digital circuit, proving that you can make a NAND gate with it proves that you can make anything else. Okay. So this notebook is pretty simple. I just wanted to show like the decision boundary bouncing around a little bit. So we are going to go ahead and run through it. And here it's a very simple toy data set. Let's see if it does like this. Sorry, give me 1 second. Oh, it's not finding this. Sorry about that. The link changed a little bit. I will go ahead and put this copy in GitHub right now before we move on so that you can get to it. Perceptrons. Okay. Okay, so that's updated with the correct link. And if you reload and then open it in Google Colab again, that will take you to the correct location. Here, we're just spitting out, okay, let's take a look at the X values and Y values. We can see that we have 20 of them. And they're arranged so that we have 10 of a class 0, 10 of class 1. Not super interesting. And then if we want to take a look at the data set that we're trying to split, it's clear that there is a linear separal boundary that lies somewhere in here. So this is the perceptron itself. You can see it as a very, very simple model. And in this case, we have just our n-dimensional weights stored as an array, or excuse me, a list in Python, and a bias. All of these are set to 0 initially. Our quote-unquote forward prediction is how we actually get the class label. So here we are just going to take this dot product between the weights and the X vector. This is a little bit larger as well. And then this is doing the Heaviside function. So if we get this weighted sum that's above 0, we return a class prediction of 1, else we're returning 0. And update here, this is the bit that's actually doing the algorithm to learn the decision boundary. So it's finding the error and updating the basically the slope of the boundary and then also the offset based on that per the algorithm we looked at earlier. So we can see here, we're just doing, okay, create a perceptron. We're going to feed it in this data point, and it says that the class of this one should be 1. And we can see that it updated the model parameters in order to do that. And then here's a simple training loop. We're just doing an error count where we loop through and we are predicting, updating if the prediction is incorrect, and then we just do that for 5 epochs. And we can see by the time we're through the 5th epoch, it's gone through the entire data set 5 times, and it is not reporting any errors for classification anymore. A bit more interesting, though, I wanted to watch how the decision boundary is actually bouncing around. So here what I'm doing is just shuffling the data so that we don't have all of the negative classes followed by all of the positive classes, and then splitting it apart again. These are 2 functions where the train and visualize, all I've added here is we're doing a call to the plotting function every time we run through a training point. And then this is a very similar plotting function. This code here is what is actually calculating the decision boundary to show it on the plot. Okay, so if we just run this now, it's going to print out all of these just directly one after the other. And you can see that the decision boundary is not changing when we don't have an error. But when we do get an error, that's when it bounces around to try and fix that problem. So you can see this is just 1 epoch. We went through the entire data set once. It made 3 errors, so we saw it change 3 times. And at the end of this, it is still incorrectly classifying 1. So the algorithm would tell it, you need to go and do this again until you classify this point correctly as well. So the way that this will run is going to change also depending on the order of your data points. You might run into more errors or less. It might take more or less time to converge. It's just randomness in how the data is coming to this algorithm. To my wiki page. So neural networks, we take this idea of perceptrons, but now instead of just passing it through this one threshold function, so we have the output of the neuron thresholded to 0 or 1, we're going to feed that instead into a nonlinear, what's known as an activation function. And just this will allow us to perform a bunch more tasks. We can do classification still, but we can do multi-class classification. So not just 0 or 1, we can do any number of classes. We get to do regression, dimensionality reduction, function approximation, which is, kind of a generalization of regression, and a lot more learning tasks. So it's been known since, I do not remember exactly when that theorem was put forward, but multi-layer feed-forward networks are universal function approximators. With enough training and enough complexity, you can approximate any function that you would like with a neural network. So neural networks are basically the ones that we're going to be talking about today. They're fully connected. They have some number of neurons, and every single neuron is going to be connected to everything else. So here, sorry, this is not that easy to read in person, but this is just our input vector. So in this case, we have a 5-dimensional input vector, 5 features for our data point. And then it's fully connected to initially 3 neurons in one layer, the first hidden layer. And it's hidden because we don't observe these states. We only observe the input and the output. So we feed into the first one, and then we connect all of these 3 neurons into 5 neurons in a second hidden layer. And then that gets collapsed down to an output. So because it's just this one single scalar value for the output, this is a regression task. If you wanted to do a classification task, you would instead have 1 output neuron per class that you're trying to classify. And then this is not super hard, it's just a bit of notation, but the way that we are noting the weights here, the first subscript on the weights is indicating basically the number that it's associated with. So it's the 5th element of the previous layer. And then the second subscript is the 3rd layer or the 3rd neuron of the second layer. So 5-3 just means, okay, we're connecting input 5 with our neuron 3. And the superscripts are showing me, okay, what layer am I associated with? This is layer 2. The input is 1. First hidden layer is technically layer 2. And then we can see that this one is doing, okay, now we're inputting, this should be the other way around, excuse me, 3, 5. So it's connecting neuron 3 to neuron 5, and it's associated with that third layer. So in this one, it's a pretty simple neural network, but we're already up to 44 parameters. So we have 15 weights here and 3 biases, 1 bias per neuron, and then 15 and 5, and 5 and 1. So this is, like, again, this is incredibly simple, and we already have to learn 44 parameters for this thing to work. So modern neural networks, these have trillions of parameters to learn, like all of the new neural network architectures that you hear about, ChatGPT, trillions, and it takes months to train all of these. And then I want to give a quick note about how you would do classification. So if you have 3 classification tasks, instead of just the single output, you'd have 3 neurons. And what those are going to say is, okay, the first neuron is saying how much I am activated is how much this network thinks that this input is class 1. And similarly for 2 and 3. So you need to perform a one-hot encoding where you just say, okay, for my 3 outputs, which one has the highest activation? And then I'm just going to say that is the class, set that instance to 1, and then the other one's to 0. So that's how you get your prediction. And then 2 other small notes when you hear about people talking about networks. As networks get quote unquote wider, what that means is that the number of weights per one layer is actually more and more. So it's like lengthening out vertically in this picture. Whereas deeper means that you're adding more and more layers, hidden layers in between your input and your output. So the activation functions are really what makes neural networks interesting, though. So I'm going to talk about 2 very common ones. You can use any activation function that you want, but these ones are very commonly used because, and especially with rectified linear unit, it's because it works very well. So this first one, this is known as the sigmoid function, also known as the logistic function. It's called a squashing function, which means, okay, we can give it any input in the entire real line, and it's going to take that and map it into 0 and 1. This has a helpful additional, we can observe that, okay, 0 and 1, that's also the range of probabilities. So we're just going to interpret that as a probability. It's not truly a probability, but we can interpret it that way. So for classification tasks, this is how you can take those activations and turn it into a probability of a class, and then do the one-hot encoding on the probabilities. And then one reason I say it's a pseudo probability is, for 3 classes, you should have your probability sum up to 1. But you can have neural network activations where, for example, for 0.1 or class 1, it says, I think it's 70% class 1, 60% class 2, and 10% class 3. So that's not a true probability distribution, but we will treat it like one, and we'll say, okay, you are class 2 then, because that's the highest activation. Then one more note. So notice here that as we get really, really small, like very negative or very positive inputs, the function has leveled out. There's no more gradient. So changing a little bit right around 0 makes a bigger difference in the output of your function than changing a little bit in high positive or negative areas, which is fine if we want to use this to create pseudo probabilities, but it can be problematic in the middle layers of a network because we need to train. So I'll be talking about that a bit more in about 5 minutes, I would think. And then we have this rectified linear unit activation function. So this kind of acts like the thresholding function and a linear function together. If you're negative, it just sets you to 0. And if your input is positive, it's going to scale the output linearly with your input. And then as you're in this positive value, you can see that like if you're changing the input and like you're changing the weight a little bit, it's going to, if you're at really, really positive values, or you're just at kind of like small positive values, it's going to change the output by the same amount. So you have this nice gradient that is just the same throughout this entire space. Okay. Okay, so we've talked about how do you set these you can set a neural network up, you can connect them, you can put all of these activation functions, but how do you actually train it so that it's giving you good outputs? You actually want it to be able to come up with scalar values that are representative of the function that you're trying to get at. So the way that we do this is just first you randomly assign all of the weights and biases of the entire network. So you just have some starting point. And then what you're trying to do is make changes to all of these weights so that it's going to start to more and more approximate the function that you're looking at. So the first thing that we need to do is basically figure out, okay, we've assigned all of these random biases. How far away are we from something that is actually what the output that we want is? And you can get at that with a loss function. So here, I'm just showing one example of a loss function, which is saying, okay, I have a predicted output. I took this input and I just fed it through my completely randomized network, and I get this predicted Y value. Let's say it's like 15. And then I know that the actual value for the Y is 5. So if I just take the L2 loss, that's going to be 100. Yeah, because you're just taking the difference between the two and squaring it. There's also, as with neural networks, a lot of it is engineering and kind of art as much as it is science. So there are a ton of different loss functions that you can use. L2 is very commonly used, but it's certainly not the only one. And this is actually a function of our weights and biases because the predicted value changes with our weights and the biases, which is good. So we're looking at all of our data. If you sum it up over the entire data set, you get just some value. And that becomes an optimization problem. We know what it is outputting, we know what we want it to output, and we can change these features. So we need to push the loss that we're getting closer and closer to the true value. Okay. So talk about optimization. Very simple optimizations are very nice, like like if we have a convex function, this is just very simple. We know it has a global minimum, and we can just say, okay, we start up here, we follow the slope down until we get down here to 0, and we say, okay, great, we have achieved the global optimum. We cannot get anything that is better than this. We're done. That is not at all what is happening in this case. We have non-convex cost functions, which basically mean we can have many, many, many local minima. And furthermore, it is very, very hard to find a global minima. We have to be settling for one of these local minima. So, our baby neural network has 44 dimensions. A very simple neural network that we'll see later that's just classifying a 28 by 28 digit is going to have on the order of 10,000 parameters. So this is a really, really high dimensional space. It is not feasible to be able to look through the entire space to find the true global optimum. So instead, what we're going to do is we say from our randomized start, we just need to follow the slope down and end up in a local minimum. And then we're going to basically see if the accuracy there is enough. And you can do multiple tries because you'll get different starting points. But we are just going to find a way to basically follow this surface down until we hit one of these local minimum down here. So that process is known as gradient descent. So the way that gradient descent works is essentially, like I've been saying, we're just following this surface, and we want to take steps down into these little valleys. So we can do that because of the way that these are set up. Basically, we have these like nested function applications. So this first layer here is applying our output, which I just showed here as a little sigma of this. So it's just taking an activation function of the weights times our input plus the bias. And then, so basically everything coming out of here is represented in this function. And then the second layer is taking that as an input to its weights. So here, this is coming out of the second layer, the first hidden layer, and it's getting multiplied by all of these weights here. And then it has these biases added. And then that goes through just another activation function. So we just apply a second one. And then that just continues going. So you can do this as many layers as you have. What that allows us to do is if we're trying to work backwards, then we can simply do the chain rule to it. So from calculus, the chain rule is just you have a function of another function. What you can do is take the derivative of the first function times the inner function, and then the derivative of the inner function. And all we're doing when we're calculating basically which direction to tune these weights and biases is we start here, we apply the chain rule so we know how to change this one. We apply the chain rule again, and step one we're back, and we know how to change all of these weights and biases. And then you just go back propagate all of these different values back through our neural network. So that's making the updates. Here. Okay. So that's how we're kind of stepping around in our gradient to try and move downwards. There's a couple of different ways you can do that. Like there's so many different ways that you can optimize, but there's a couple of ways even if you're just looking at gradient descent. So one thing you can do is what's called stochastic gradient descent, where you just take one example, you feed it forward, you calculate the loss, and then you do the chain rule backwards to back propagate all of those errors. So per example, you're just taking one step down. This can be a little bit problematic if you have, like, for example, a pretty nicely separated data set. Like, let's say you have all of your positives over here, your negatives here, but you have a positive right in the middle of this. So maybe it's like a spurious detection, or there's something wrong with your data, or it's just like a really like high outlier. But if you do stochastic gradient descent where you have this positive here, it's surrounded by negatives, then your network is going to work worse on the next negative that's really close to it, because that got adjusted in the opposite direction than it wanted to, basically. So that randomness is adding some variance to the direction of the steps that you're taking in your quote unquote true overall loss function. So another way that you can do it is say, okay, I don't want to do one by one like that. I just want to do every single data point at once. So you would calculate the loss for your entire data set and then take a step in the direction of the gradient for all of them together. So very low variance in terms of the direction you're going, but very computationally expensive, because now every step, if you have a data set of like 100,000 training examples, you have to do 100,000 forward passes to get that. Instead of just for stochastic, you have to do one for each forward step. And then the last one is, okay, we have this like mini batch descent where it's kind of a balance between the two. You have maybe 100,000 training examples and you split them up, and maybe you're doing 5,000 points at a time. So by taking more points, you reduce the variance. You're not going to get these weird outliers that are pushing your neural network in the wrong direction. But it is a little bit more computationally expensive than just a single point per optimization step. Okay. And then there are just like so many different types of optimization schemes, even just ones that basically take gradient descent and try and extend it. So I thought this article was really good. I have used this pretty extensively, and I wanted to show specifically, he has this really nice, basically explanation of, that's momentum instead. It's a really nice GIF that is basically showing like the different steps that you're taking forward. Okay. So here we have this like higher dimensional space that's being projected down onto 2 dimensions. And you can see the little paths that are coming out of our starting point. There's these different optimizers with different methods, and they're all taking different steps. And you can see that they are reaching the global minima that they're all looking for at different rates and taking different paths to get there. And a lot of that is just heuristics about how am I trying to set it up and which way do I want it to go, and different things. But there are plenty to read that we can't get to today. Yeah, so you can see we've talked about stochastic gradient descent, and it's this red ball is just very slowly making its way, but generally going in the fastest direction, like directly down the contours that you would want it to be going, just straight down. Yeah. And then at an even higher level, so we've talked about just the parameters of the network. That's the weights, the biases, everything that's actually baked in. It's doing the calculations. There's also a concept of hyperparameters, which are, these are things that you can tune that also basically influence your neural network, but aren't actually part of the math that's like under the hood. So one example of that would be the learning rate. So for stochastic gradient descent, you can basically tune what the step that you're taking along your gradient that you just calculated. You can basically say, okay, I want to take a really large step or a really small step or like somewhere in between. And the learning rate is how you change that. So if you change your learning rate so it's really, really high, you're going to be taking very large steps in your gradient. But what that can do is actually maybe overshoot the local minima that you wanted to get to and send you flying off in some other direction. So it can make it hard to converge. Whereas if you're taking really, really tiny steps, you're converging very slowly, when a larger learning rate would probably get you to the endpoint faster, like half as many epochs or something. So something that you can change that's going to change how fast your training is. It could also change what local minima you end up finding, but it's not baked in the network itself. It's just like during the training or something like that.
Can you modify the learning rate like during the process, or does it?
Yes, absolutely. So that would be something like cosine annealing, where it takes a learning rate and it says, okay, we're going to take a learning rate for every sample, every mini batch, whatever you want, and it's going to just sample from a cosine curve. So it'll start out trying to go really, really quickly, and then it's going to slow down and hope that maybe it's in a valley somewhere. And then if it's not working, it's going to try and step out of that area and find somewhere else. Yeah, so just absolutely tons of different things you can think to do with it. Okay, so that's everything finally for the theory portion. I have 2 more notebooks here. We're going to go through 2 neural network examples using PyTorch. And the first one's going to be, okay, let's get a neural network working with XOR. I think I actually already have this open, so let's just go there. Yes. Oh, sorry, let me put that link in the chat as well. Okay, so here we're working with a different data set that's just a kind of fuzzy XOR. So let's get down to, I encourage you to go back and look at some of this later, but we don't have time to talk about like all of the NumPy, matplotlib stuff. Okay, so this kind of fuzzy XOR data set where it exhibits lack of linear separability, and then there's also kind of some actual overlap in between the classes themselves. So you have some of the points like this one where it's right on the boundary between what you would expect for class 0, class 1, etc. So what our neural network is going to have to learn is some sort of like saddle point where it's kind of sweeping a decision boundary in here and then back out the side and on this side as well. So pretty complicated nonlinear behavior. But thankfully, PyTorch makes this really, really easy to implement. So this is probably the first time that you guys are seeing it. Let's take a look at this class. So it's just inheriting from what Torch calls a module, which is like some sort of chunk of functionality of a neural network. The initialization method is when we are going to tell it, here are the layers that we want, and here's how we want them to be organized. So we're telling it, okay, these are going to be sequential, which is just, one directly after the other. Our first layer is going to be linear. The input size will be the number of features in the X feature vector, and then it's going to have an output of 25. So it has 25 neurons in this first layer. And then we tell it, and then you're going to feed that through the rectified linear unit activation function. And then similarly for the second one, although for the second one, you can see that now we're taking in inputs from 25 neurons down to 15. And then we go from these 15 down to just the number of classes, which in this case is 2. So we'd have 2 outputs. And forward is essentially our inference step. So we're saying take X and feed it through, and you're going to get these logits out. So you can see we're calling self all layers, which is just, it's going to feed it through every one of these in the order that they're listed here. So, okay, ran that. Another thing that PyTorch gives you is this data loader functionality. So what this is doing is it's taking, okay, we have this data set. You put that inside of a class, and then the data loader is going to handle iterating over that class for you. So you can see this data set, we have some features and some labels. So the features would be our X vector, labels is the Y, and we can tell it, this is the type 32-bit float for the features, and then 64 int for the labels, which is probably overkill. And then you can see the get and set methods are simply like it's going to return as X and Y, the features and the labels, and it also defines a length, which is the length of the labels. And we split these up into train, validation, and test and define 3 different data loaders. So we have one data loader that its entire purpose is it's just serving out training samples. And then you've got another one for validation and test samples as well. And then also having training and test is it's very important to keep these completely separate because you want to make sure that whatever you're learning over your training data is actually generalizing to your test. And you can't do that properly if your test data was seen during the training procedure, because it can just memorize what to do for that point. Okay. Okay. So for computing accuracy, oh yeah, that actually was right. So what we're doing here is just defining a function that's going to take in our data loader, run over the entire thing, and tell us how many of these samples the neural network got right or not. Pretty simple. So we put it into evaluation mode, so it's not going to be updating the weights or anything. You can see here that we're just enumerating through the data loader, and we're getting features, labels, and the index of it out. And then this is just, okay, the model takes in the features, gives you your predictions. So the logits get fed into, this is doing the one hot encoding here. And very simply just taking, okay, the number that we got correct over the total number that we did. Okay, so this is the training part. I'm just going to set the seed so that every time you run this, you get the same results. You can try changing the seed around a little bit and just seeing how much it's changing, because changing the seed is going to change the initial weights and biases of the network. So it's starting out from a different point in the loss function. And you would expect to see slightly different accuracies or things coming out of the end of this training procedure. And here, the optimization that we're using is the stochastic gradient descent. And we are actually setting the learning rate hyperparameter to 0.05. That's a pretty typical value, like 0.05 would be 1, 0.001, things like that are pretty commonly used. And here we're just going to tell it, okay, no matter what, you're just going to run over the entire data set 10 times for your training procedure. That's the number of epochs that we're setting there. And then to do this, we put it back into training mode. And then this is just what we've seen before. We actually run the features through the forward pass. Here they're using a cross entropy loss instead. And this bit is implementing, okay, we have our stochastic gradient descent optimizer. So we're going to, like every neuron stores the last gradient that it had. So you need to tell it, okay, we're restarting. This is a new one. So just zero out the gradients, do the back propagation, and then take all of the weights and step them along the direction of like biggest increase for this single sample. And also we'll print out some of this useful information while we're doing it. So you can see like it's just going through and it'll show you it's pretty high right off the bat. I think it's, oh, there we go. Okay. So you can see where it's starting at. We have at the end of the first time we've gone through all of the data, we get to a training accuracy of about 70% and validation of 65. So there's a slight difference where it's a little bit at this point overfit to the training data. But by the time we get to the end, we have already hit like 98% accuracy. And then I just wanted to show, okay, the decision boundary. This is just after we have the trained model, essentially what this code is doing is it's just querying for every point in this space, give me a prediction. So you can see that it is switching from this like orange class label to a blue class label and then back to orange. So you can see exactly where it would change based on the input. the class. And adding those nonlinear activation functions is what is giving us this nonlinear decision boundary. Okay. So that's our XOR example. This one out, and then I'll put up the MNIST example. Okay, this one is a little bit nearer and dear to my heart as somebody who works on computer vision problems, because what we're going to be doing is, let me actually show you what the data looks like. We get to it eventually. So it's downloading everything. I think it has like 60,000 samples in this one. But so in the meantime, while this is running, I'll take you to MNIST. Okay, never mind. Okay, so these are the images that we have, and they're just like small, maybe 20 by 20 pixels, maybe it's 20 by 28, but this is our training sample. Right now, everything's organized nicely so that as humans, we can look at this and say, okay, that's a 4, that's a 7, because it's like 20 by 20. But what we're going to end up feeding into the neural network is we're going to take these and then flatten them out. So they're just like one long array. And then the array is going to be full of like, okay, this is a black pixel, this is a black pixel, until it gets to, this is kind of gray, this is white, this is white. So we're just flattening it out, and that is how we are forming the input for this neural network. Some more notes, like a really good place to start whenever you're doing like tasks like this is just do the one, like, okay, what is the absolute minimum type of accuracy that I could get? Like if I'm doing worse than this, I'm actively doing something wrong, is just take all of your samples and say we have, 1 through 9 here, and 1 is the most common class. So the dumbest thing you could do is just say everything is a 1, and I will be right 11% of the time. So that's like a very, very basic, like absolute baseline of performance. Like you are literally just guessing. Yeah, and then that comes out of the fact that like we just don't have the same number of samples across 0, 1, 2, et cetera, all the way up to 9. Okay. So the shape, yeah, so it's saying this is a 28 by 28 image. And it's 1 value. So these are grayscale images. Typically with images you would see, because it's an RGB, it's 3, because you have one channel for red, green, and blue. And then the batch size here is just saying, okay, for every batch, I have 64 of these. So I'm going to train on 64 images at once. And this is going to just smash everything out so that we have this one long feature vector to feed into the neural network. And the neural network here is still really simple. It's actually the same as what we saw for the previous one. We're just giving it more neurons. So now the first linear layer has 25, and then that's going to collapse back down, or excuse me, the first one has 50. It'll collapse down to 25 neurons, and then it's going to go out into 10 neurons, 1 for every class, 0 through 9. Okay, so this looks the exact same. And again, we're just going to be using this stochastic gradient descent optimizer, the same learning rate. And check out, this is going to take a lot longer to run, just because it's a larger data set, and the data is larger, the neural network is larger, but it's still running pretty quickly. So going from our just max class-based classifier, even after just a single iteration, we're already hitting 88% accuracy on these on the images, which is just insane because it's a pretty small this is a pretty small network as well. And then after the second epoch, we can see that it hit 92% training accuracy. I think I just have the graphs for this. If you are interested, you can come back in here later, and some of the things that you can play with is you can change the learning rate to see if you can get it to converge faster or slower. You can change the cross entropy for the same thing. There are a bunch of things here that you can play around with just to get a feel for it. And then 97%. So you're typically will see that it's making very, very large gains in accuracy early on, and then it's going to kind of level off the further along you get. So this is from a previous run that I did. It eventually got to a 97% accuracy. And then one of the other things that you can do with PyTorch is basically just visualize what's happening over time. So here we can see that our mini batch loss, this is the actual, so it runs, the 50 or whatever samples compose the mini batch through, calculates the loss. And you're expecting to see that this is going to decrease over time as your network gets closer and closer to figuring out what function goes from these, 28 by 28 images to one class label. But again, because we have this because we're doing this mini batch, it's just a sample of our larger, this larger data set. It's not actually going down very smoothly. The variance in the mini batch is going to cause it, depending on which samples you pick, where you are in your loss space, the loss can jump around significantly, but we can see that the average is still going down. And then the accuracy as well, this is just calculated once at the end of each epoch. We can see that at the start, these are going up pretty much in the same, they're gaining accuracy about as quickly as one another. And then there starts to be this kind of area where they're coming apart. And that's just the network is starting to detect some patterns in the training accuracy that is overfitting that are not present in the validation set. So that's where you sort of see these, they start to diverge from one another. And you want to stop training basically when your validation accuracy starts to level out. You can see that the training accuracy will still be increasing, but you don't want it to overfit the training set. As soon as your validation starts to level out, that's when you want to stop and see, okay, how is it performing on the test? How is it performing on the test set? And then I like this one. This is just, we're pulling up some of the incorrectly classified labels. So if you pass it through and it says, okay, I thought this was for example, it's saying, I thought this was a 0. It's actually a 6. You can see where it might be getting confused. Similarly for all of these, so.
Again, you're using that in the array when you're thinking about when it goes from. Yeah.
Yeah, so for example, this first row here, that would be the first bit of the array, but then it's one-dimensional. So rather than, you don't have this wrapping effect, it would just be this pixel, and then there's a bunch of white, and then another pixel. So we'll talk about this later in the semester. We're going to talk about convolutional neural networks, because one thing that the neural network is not picking up that you could be is that you want this spatial information. You want to know how the pixel is connected to everything right next to it. And the neural network right now is just treating these as it doesn't have any sort of idea about how these relate spatially. It's very important information to understand when you're understanding images. So convolutional neural networks make some changes to this architecture that incorporate that. Stay tuned 2 weeks from now. Okay. That is all I have. If there are any other questions, please go ahead and put them in the chat.